क्या हो रहा है? जैसे ही मैं स्टार्ट कर रही हूँ रिकॉर्डिंग वैसे कनेक्शन लॉस्ट हो रहा है. Okay. So is my screen visible to all of you?
Yes, ma'am.
Okay, so good evening all of you. Today we are going to discuss about the tutorial lecture 5 of Introductory Organic Chemistry Part 2, which is a NPTEL platform course, and the course instructors are Professor Harinath Chakrapani and Professor Nileja Dashaputre from ICEL Pune, and I am Simran, your PMRA teaching assistant. So I have taken till now 4 lectures. So I hope till now everything is clear to all of you, every question. I have uploaded all the videos on my YouTube channel. You can access that and you can saw that videos again and again. If you have any doubt, any query regarding that videos, please let me know. Anyone has any doubt regarding the previous lectures? Okay, if there is no doubt, then I am moving forward towards week 5, that is enols and enolates. So we are going to discuss about enols and enolates today. So guys, I'm starting up with problem number 1. So the problem number 1 is asking which of the following reagents can deprotonate a hydrogen on a carbon in the alpha position of a carbon. So you have to figure it out which of these four reagents can deprotonate the hydrogen which is present at the alpha position of the carbonyl carbon. That means these are the two carbonyl carbon, that is aldehyde and ketone. So you have to figure it out that which of these reagent can abstract the proton from this position, that is the alpha position. So you have to figure it out that which reagent can deprotonate a hydrogen from the alpha position of the carbonyl carbon, right? So this is the alpha position. So the first option is triethylamine, second is lithium diisopropylamide, third is sodium hydroxide, and fourth is acetate ion. So guys, first of all, I want to tell you that this alpha hydrogen of this carbonyl compounds is not that much acidic, and that's why this pK value for this is high. So the I told you about the pK and Ka relationship. So if the pKa values are high, then the Ka value is low. That means that the acidity of that proton will be low. So here also in the carbonyl compounds, the the value of Ka, that is the acidity of the protons at present at the alpha position of the carbonyl carbon, is not that much high. That is why you need a strong base. You need a very strong base to deprotonate the hydrogen that is present at the alpha position of the carbonyl compounds. Okay. So these are the four base they have wrote. So now in which like among these you have to select one base that is very much strong which can deprotonate the hydrogen. So can anyone tell me among these which is the strongest base?
Lithium diisopropylamide.
Yeah, LDA, lithium diisopropyl amide. So this is the strongest base in between these four. So you need the strongest base to deprotonate the alpha hydrogen. So here it is mentioned that the alpha carbon of carbonyl, the hydrogen which is present has a pK of 16 to 18 in the case of aldehyde, whereas in the case of ketone, the pK lies between 19 to 21. So guys, triethylamine, that is a base, that is a weak base, has a pKa value 10.8. Sodium hydroxide has a pKa value 15.7 and acetate has 4.76. So I have told you that higher the pKa value, lower will be the Ka. That is the acidity. So higher pKa, low acidity. So in the case of triethylamine, sodium hydroxide and this acetate, this pKa value of sodium hydroxide is high. That means the acidity for this is very low. That means the basic nature of the sodium hydroxide is higher. So here you need a very efficient base to deprotonate the proton that is present at the alpha position. And you can see here that LDA only has a pKa equal to 36. That means it is having a low acidity but higher basicity. So higher the basicity of this base, higher is the potential of this base to abstract the alpha proton of the carbonyl compound. So that is why lithium diisopropylamide is the correct answer, which can deprotonate the hydrogen at the alpha position. So is it clear to all of you? Is it clear? Any doubts, any queries? Okay, so if it is clear, then I am moving forward. Problem number 2. So in the problem number 2, they're asking what will be the major product of the following alkylation reaction. So now you have to find out the product after this first and second step. So here the alkylation reaction is happening, they have mentioned, but you have to find out the product. So one by one we will discuss the steps. So here they have added N tertiary butyl lithium. So basically N-butyl lithium and dry THF they have added. So what will butyl lithium do? First of all, what is butyl lithium? It is a base. So butyl lithium is a base. So now what will a strong base do? It will deprotonate acidic hydrogen from the system. So it will take up a proton from the system. So now there are two possibility of the acidic hydrogen which is present. See here, these hydrogens are also acidic and these hydrogens are also acidic, right? So can anyone tell me which hydrogens can be deprotonate by N-butyl lithium, which is having a higher preference of deprotonation? A or B? A protons or B protons?
A protons.
A protons. Okay. Anyone having another answer? Okay. So let us see what will happen one by one if the protons is getting abstracted from A side and as well as B side. Okay. So here you are saying that A protons are acidic enough. But now guys, you have to also notice that if a negative charge is getting generated at the alpha position of this nitrogen, so will it conjugate with this that much? Because if it will go here, you also have an idea that the nitrogen is also having the lone pair that is present, right? So there will be a very steric crowding that would be present at the nitrogen, as you know that nitrogen is an electronegative atom and has a tendency to occupy the negative charge, but the steric crowding at this nitrogen will be higher if this negative charge is getting generated. This will not delocalize here, as if it goes here, the nitrogen lone pair is not going to participate in a delocalization, right? So there is no delocalization if alpha proton has to be removed. But if a proton is getting removed at this position, right? Then what will happen? Now it will go here and it will go here. As I've told you already that the nitrogen has a tendency to occupy the negative charge, right? So here also, after going at this position, a negative charge is going to be generated at the nitrogen. So nitrogen being electronegative, it will stabilize that negative charge on nitrogen. Okay. So here there is a delocalization that is possible in the case of B protons. But there is no delocalization that is possible in the case of A protons. That is why the acidity of these HB and also the formation of negative charge at HB center is more facile than HA center. So deprotonation first will takes place from the HB center due to the delocalization which is present in the system. So is this much clear to you why the hydrogens is going to deprotonate from HB position, not from HA position? Is it clear? Is this much clear to all of you? Can anyone respond, please? Is the deprotonation why it is taken from HB position rather than HA position? Is it clear to all of you? Am I audible? Shit. Sorry guys, I just lost the connection. Now my screen is visible to everyone. Can anyone tell me, did you guys hear what I said? Why the deprotonation is happening from this position, but not this position? At that time, I was audible or not? Can anyone tell me? Am I audible, guys? Oh, what the hell is going on? Guys, am I audible?
Yes, ma'am.
Audible.
Audible.
Screen is
Okay. So can anyone
screen
tell?
is not coming.
Okay, so can anyone tell me what I have explained on this first step? At that time, I was audible or not? The HB protons is getting eliminated rather than HA. Am I audible at that moment?
No, ma'am.
Okay, so I will to explain again. So here, what is happening, guys? See, we have two acidic protons. So we one by one discuss about one and second step. So in the first step, they have added butyl lithium. So butyl lithium being a base, so it will abstract the acidic proton, right? So acidic protons has two possibility. Here also you have the acidic protons, and here also you will have a acidic proton, right? So we have discussed, and someone of you has said that yes, Ha protons should be eliminated. But here what is happening, guys, that if you will remove protons from Ha position, so there is a negative charge which is getting generated at the alpha position of nitrogen, right? But now what is happening? There is no delocalization which is present in this case. Why? Because the nitrogen lone pair is also present here, and this is not going to form a tertiary like alkyne bond here, right? So there is no delocalization that is present in the case of when the deprotonation is happening at the alpha position. But if the negative charge is going to generate at this position, then what will happen? It can delocalize here and it can go on the nitrogen. So nitrogen being a electronegative atom, it can accommodate that negative charge, right? But it would not prefer to gain a positive charge, right? So that is why here the delocalization is present in the case of Hb protons if the deprotonation occurs at the beta site. But at the alpha side, what is happening? There is no delocalization. The negative charge is not at all stabilized at that position, and that is why your butyl lithium will abstract that proton which give you a negative charge that is stabilized. Right? That means the B protons are now acidic enough than Ha protons. That is why base will abstract Hb protons rather than Ha protons. So is this much clear to all of you? Why the abstraction is happening at Hb protons? Shit, yaar. What the hell is happening? क्या हो रहा है? चलो फिर मुझे one second. I'm really sorry, guys. Today the network is so slow that so I'm using my net now. So we were here. So connection was lost before I explained this. So here if the negative charge is getting generated at the HB position now, then what will happen? There would be a delocalization that was happening at this position and nitrogen will get a negative charge there, right? So nitrogen being a electronegative atom, as I have told you guys, so it will accommodate that negative charge well. But if the negative charge is going to generate at this position after the abstraction of proton, that is the alpha position, then what will happen? There would be no delocalization that would be possible because now it was having a lone pair of protons, and if this goes here, this lone pair has to go here, and a triple bond is getting generated, which is not possible in this case, right? So that is why the delocalization is not happening in the case of alpha proton abstraction. Why? It is happening at the beta proton abstraction case, right? That is why the butyl lithium being a base will abstract a proton from the beta position rather than the alpha position. So is it clear, guys, now why the abstraction is taking place from the beta position, not the alpha position? Is it clear?
Yes, ma'am.
Okay. So if it is clear, then the negative charge is now generated at the beta position, and what will do it will do in the second step, it will attack on this R group and Br get knockout. So now tell me which is the correct option, guys.
First one.
First option. So option number 1 will be the correct one, right? Okay, so I hope it is clear to all of you. So now moving towards the problem number 3. So in problem number 3, what is happening? They are asking the major product X formed in the following reaction condition. So you have to identify the product X which is going to generate from 1 and 2. So first case, they have added one equivalent of LDA at minus 78 degrees centigrade. So I have told you LDA is a very strong base, so it can abstract proton from the alpha position of the carbonyl compounds, as we have seen in the case of problem 1. So here also the similar concept will arise, and now LDA can deprotonate the proton at the alpha position of this carbonyl carbon. So here there are two proton that is present in the system. Two alpha protons are present, right? Two alpha positions are there. So can anyone tell me which hydrogen should be abstracted at minus 78 degrees centigrade? Is it hydrogen A, that is proton A, or proton B?
B1.
Proton B. Okay. So why proton B, guys? So see here, what happens at minus 78 degrees centigrade, that is a low temperature is there. So at low temperature, a kinetic enolate is going to be formed rather than the thermodynamic enolate. What is meant by kinetic and thermodynamic enolate? So here what will happen after the anion generation at this position, see what is happening. After the anion generation at this position, here it will delocalize and form a double bond at this position, right? And as you know that double bond is stabilized when it is forming between the more substituted carbons, right? But here it is forming at less substituted site. That is why we are saying that it is a kinetic enolate. It is a kinetic enolate because the double bond which is getting generated is forming between a low substituted site rather than the more substituted site. It is forming at the less substituted site. That is why it is known as the kinetic enolate. But if you abstract a proton from this position, then what will happen? The double bond is going to generate at this position. So it is more substituted double bond, and according to the Sidzeff rule, more substituted double bonds are more stabilized. So here a thermodynamic enolate is getting generated. So guys, kinetic enolate is going to generate at low temperature, but thermodynamic enolate is going to generate at high temperature. So this is how you have to keep in mind that temperature has a role in abstraction of proton in case of LDA. In both the cases, if you are using LDA but the temperature is different, then kinetic and thermodynamic enolate has a competition. So if the temperature is low, kinetic enolate is going to be formed, but if the temperature is high, then the thermodynamic enolate is going to be formed. So in our case, in this question, the temperature is in minus, that is a very low temperature. So at low temperature, the kinetic enolate is going to be generated. So a less substituted double bond is going to be formed here, right? So this double bond is going to form. So this is how it is happening. LDA will abstract a proton from here. It will go this side, and a less substituted double bond is getting formed. So after that, after the formation of the less substituted double bond, after the formation of an enolate here, the second step is the alylation. So what will happen? Now the enolate will come down and it will attack to this carbon rather than this carbon, because it is a sp2 hybridized carbon, and it will this CBr bond is has a short bond length rather than this CBr bond that is attached to the sp3 carbon. So it is very facile to be knockout rather than this carbon. That is why this bromine is intact, but this bromine is knocking out. So here it will attack on the more exposed sp3 CBr bond, and bromine will knock out to give you the product this. So now the correct option will be, which is the correct option? Option number
B,
B. So
B,
option number
B
B
is the
will be
minimum.
the correct one. So is it clear to all of you this question? Okay, so if it is clear, then I am moving towards the problem number 4. So guys, in problem number 4, it is somewhat similar to what we have studied till now. So they are saying that identify the major product of the following condensation reaction. So now you have to identify the major product of the following condensation reaction. So here in this molecule, they have treated in first condition. This should be the second condition. No? So in first condition, they have used sodamide with methyl iodide. So sodamide is a base. We have talked about it in when we are learning about the nucleophilic substitution reactions, right? So sodamide is also a base, but it is. Can anyone tell me the sodamide is a base? Is a strong base than LD or a weak base than the LDA? Hmm?
Strong.
Sorry,
Stronger.
stronger than LDA. Are you sure? So here, what is happening, guys? Sodamide case, we will have a negative charge on the amide, but in this case, lithium diisopropyl amide, this base is also strong enough. Here, this is a nucleophilic base, but here LDA is a non-nucleophilic base, right? So now they have treated first sodamide methyl iodide. Sodamide is not that much strong than LDA, but that it is little bit weak than LDA. So what will happen? Here they have given you the pKa values of both the acidic protons. So now they have said that the pKa of this NH bond is 17. I have told you that if the pKa is high, then the Ka is low. So that means the pKa value of these protons are high. That is the alpha protons of the carbonyl carbon. So it will be having a acidic, that is the Ka value, which is pK is higher and Ka is lower. So the acidity of these protons is lower than the acidity of this proton that is attached to the nitrogen. So nitrogen containing proton is acidic enough, but these alpha hydrogens are low in acidity. So that is why if you treat it with sodamide and methyl iodide, then the less, the more the more acidic proton will get abstracted rather than the less acidic protons. So sodamide being a weak base than LDA, so here the abstraction will take place from the lower acidic, sorry, the more acidic side. So which is the more acidic side? So where should this methyl iodide should add?
Nitrogen.
Yeah. So nitrogen will take up this methyl because sodamide will abstract the proton from NH because of the higher acidity of this proton. Because it is a weak base than LDA, it will abstract a proton which is higher in acidity. So NH being the higher acidic proton, it will abstract this proton and it will become N minus. This nitrogen will become N minus, and now it will attack to methyl and iodide will knock out to give you NMe. So here Me will get substituted in our case, right? So now in the second step, they have added LDA and ethyl bromide. So now what will happen? Which protons are abstracted? Which protons are abstracted, guys? The protons at the alpha position of this carbonyl carbon. So it is getting abstracted. So one of the proton is getting abstracted by LDA, and a negative charge is formed at the alpha position. And now this negative charge will attack on the ethyl bromide and Br will knock out. So now tell me which is the correct option among these four.
B is the correct option.
Option number B. So option number B will be the right one. Okay. Is this clear to all of you? Okay. So if it is clear, then I am moving towards the problem number
Yes,
5.
ma'am.
So in problem number 5, they are asking what is the final product of the given reaction occurring via the silyl enol ether intermediate. So what is the final react product that is given by this reaction? So you have to identify this, and they have given you the intermediate, that is the silyl enol ether. This is the silyl enol ether which is intermediate in this reaction. So what is the reaction? So here they have treated. Someone wants to say something. Sorry,
What's your breaking?
my voice is breaking. Okay, let me switch my network. Am I audible now?
Yes, ma'am.
Yes, ma'am.
So coming back to problem number 5. So guys, they have taken a ketone and they have treated it with triethylamine and TMS chloride. So now what will happen? This TMS chloride, that is the trimethylsilyl chloride. So this is trimethylsilyl and you have to add chloride here. So what will happen here? This silicon, this oxygen basically forms a bond with silicon. So here this OSIMe3 bond will form, and this triethylamine then take up a proton. So what will happen? It will form a complex with this, and now this proton becomes very much acidic because now it has to go here and has to stabilize the positive charge that is coming at the oxygen. After this lone pair attacks the silyl and chloride will leave out, what will happen? This positive charge is getting generated at the oxygen, and the driving force is that to neutralize the positive charge which is present on the oxygen. So now this proton at the alpha position, which cannot be abstracted solely by the triethylamine as we have seen earlier, now here TMS chloride will help making the alpha hydrogen acidic by coordinating with oxygen. So here it will form this carbon more electrophilic in nature, and thereby it will withdraw the electrons from this CH bond, and here this hydrogen in turn become acidic in nature. So that is why now this triethylamine can take up this proton, and here you will get a double bond form. So this is how your silyl enol ether is getting formed. So guys, is this first step clear to all of you, the mechanism behind it?
Yes.
Okay. So if it is clear, this silyl enol ether intermediate is now getting formed. So now they have treated it with titanium tetrachloride and benzaldehyde. So here you have a benzaldehyde and titanium tetrachloride. So now what will happen? This aldehyde double bond. So whenever you have a Lewis acid in the system and a carbonyl carbon in the system, so Lewis acid will form a bond with your carbonyl carbon oxygen. So basically titanium tetrachloride will form a bond here and this get a positive charge. So now it is becoming a electrophilic carbon. So this carbon becomes very much highly electrophilic. So basically they have added this Lewis acid with benzaldehyde to activate the benzaldehyde to make the carbonyl carbon more electrophilic towards the nucleophilic attack. Okay, so now what will happen? This OSI bond will now come down and now this double bond will attack onto your carbonyl carbon. So this will get neutralized. So after coming down, this will form again the carbonyl compound and this will form a OTI bond. After hydrolysis, now your OTI bond will get OH formation. So what will happen? So if you have this bond, O-silyl bond is getting cleaved. So here what we have is at the at this position this group is getting attached. Fine. So at this position this group is getting attached. That means we are having this alcohol at this position and your pH at this position. Right? So this is how now your silyl oxygen silyl enol ether will behave as a nucleophile towards the benzaldehyde. So titanium tetrachloride will activate the benzaldehyde and this silyl ethyl will act as a nucleophile in the system to give you this alcohol, basically beta hydroxy carbonyl compounds. Okay, so is this mechanism clear to all of you?
This one.
Okay, so which is the correct option now?
Second.
Second option. So second is the correct one. Okay. So now moving towards problem number 6. So they are telling you identify the final product of the following Reformatsky reaction. So if you guys recall, I have told you about the Reformatsky reaction in the previous lecture only. Okay, so we have seen a reaction which is known as Reformatsky reaction, example of that in the previous lecture. So here also we will see this. So what is happening? You have a zinc bromide containing ester and benzaldehyde and they have done the acidic workup. So you have to figure it out what will happen in the reaction and what will be the end product. So Reformatsky reaction means you have a zinc Br which is making your alpha carbon negative, that is electronegative, and itself zinc is electropositive in nature. So there is a partial positive character which is present on zinc due to the electropositivity of zinc and a negative character that is generated at the alpha position. So basically it is useful in the case of nucleophilic attacks. So basically it will make your alpha position a nucleophilic position. So we have seen in this case that nucleophile is forming after the OSI bond cleavage, and this is how the silyl ethyl is acting as a nucleophile. So here also this Reformatsky reagent is now acting as a nucleophile because of the insertion of zinc between CBr bond. So insertion of zinc between CBr bond will generate a nucleophile at the alpha position. So if the nucleophile is now getting generated in the system, you have this carbonyl group present and also they have treated it with acid. So now I've told you previously also that acid will protonate your oxygen of the carbonyl carbon to make this carbon more electrophilic towards the nucleophilic attack. Right? So here this negative charge is now attacking onto your carbonyl carbon. So this is how it is getting attacked. right? So here they have told you that they have done the acidic workup. And guys, you are well aware that ester will get hydrolyzed in the presence of acid. So here also your ester is getting hydrolyzed, right, to form the OH, or this ester itself can behave as a good leaving group. So here, what will happen after the nucleophilic attack? There is a OH that is getting generated, because now your O negative, which is generated in the case of benzaldehyde after the nucleophilic attack, this O negative is in the acidic medium getting protonated. If the medium is basic, then we cannot write this OH. It would be alkoxy-ion only. But in the case of acid, this O negative will cannot be retained as O negative. It will abstract a proton from the acid. So here you will have OH instead of O minus. So if you have this OH present in the system, so we are well aware that there can be elimination of ethanol, which can happen in this case to give you a cyclic system, that is a 5-member system. So you will end up having a 5-member lectone instead of the acyclic system, because of the driving force of generation of a 5-member lectone, and also the neutral molecule removal, that is the ethanol removal. So that is how you will get this cyclic product rather than the acyclic product. So is this mechanism clear to all of you?
Please explain once again.
Okay, one second. Okay, so what is happening? See guys, in the question they have given you a Refermetsky reagent, that is zinc bromide. So here I have told you in the previous lecture, if you can recall, that there would be a allyl bromide kind of system, and you have added zinc in the reaction. So if you have added zinc in the reaction, then the product which is getting formed is the oxidative addition of zinc between the CBr bond. So here they have already given you the oxidatively added zinc between the CBr bond. So here, if it is added between the CBr bond, now due to the electropositivity of zinc, because it is a metal, so it is electropositive in nature. So because of this electropositivity, so similarly like a Grignard reagent. See, in the Grignard reagent, what will happen? If you have a Grignard reagent, that means basically R can be anything. This is magnesium, and you have a Br, right? You have a Br. So here also you will write that this is negative, this is positive, and this is why the Grignard reagent attack will take place, the electropositivity, electronegativity. So similarly, here also there is a positive charge that is present on the metal, and negative charge, partial negative charge, that is present on this carbon. So it will make this particular R group more nucleophilic, and here also this is acting as a nucleophile in the system. So this nucleophile will attack on the carbonyl carbon of the benzaldehyde to give you this particular acyclic molecule. Okay. In the acidic medium, this alkoxy ion, which is now forming after the conjugation, this negative charge is now getting generated at this oxygen. Na? So in acidic medium, this negative charge is getting protonated. So you will have a OH instead of O minus. So this OH now will attack on your carbonyl carbon, right? And after coming down this O minus, this OET is now getting knocked out. So this is how this cyclization of this is happening. So basically ethanol is getting leaved out. The driving force is the generation of 5-member lectone and removal of the neutral molecule. So this is how your cyclic system is getting generated. So is it clear now?
Yes, ma'am.
Okay. So if it is clear, then the correct option will be option number C. So option number C is going to be formed after the Refermetsky reaction. Okay. So I hope it is clear to all of you. So now I'm going to problem number 7. So in the problem number 7, In the problem number 7, they have asked you the stepwise synthesis to saccharin is given below. Predict the correct reactant PQ and R. So this is the forward synthesis of saccharin. So this is the saccharin molecule. It is known as saccharin. So you have to identify the reagent, that is P, Q and R. So they have given you all the sequence of the formation of saccharin. So now they have started with toluene. So in presence of toluene, they have added SOCl2 and SO3HCl. This is the acid basically. So now what will happen guys, in the step 1, the saccharin formation will take place when this acid will cleave into OH minus and ClSO2 positive. So basically this acid will cleave into this hydroxide and this acidic molecule. So basically with this electrophile is trapped through the Friedel-Crafts alkylation reaction. Because it is a toluene and a electrophilic aromatic substitution can takes place here. So this positive charge electrophile species, basically this electrophile species is getting trapped by the toluene molecule, and similarly which the intermediate which is forming in the electrophilic aromatic substitution, here also these kind of complexes, that is the resonance structure of these molecule is now getting formed, and here this ortho product is getting formed which is in major quantity. So here you will have a ortho substituted SO2Cl in toluene in the first step. So basically SOCl2 is not going to give you the dissociation between OH minus and is not going to give you the electrophilic aromatic substitution. But this acid can give you the Friedel-Crafts alkylation. So here you will get a ortho substituted product through the electrophilic aromatic substitution. So after getting this SO2Cl at this position, now the second step is they have replaced this chlorine with amine. So this is a very simple reaction. So now in the case of Q, they have used ammonium hydroxide, ammonia and ammonium hydroxide. So now what do you think? Ammonium hydroxide will do the job or ammonia will do the job of displacing chlorine by amine? Can anyone tell me?
Ammonia.
Ammonia. Ammonia will do the job. Why? Because in ammonia, basically nitrogen has a lone pair of electrons. Right. So here the lone pair of electrons will attack onto this SO2Cl, and after coming down, this Cl will get removed and this proton, because now the nitrogen will get a positive charge. So now this positive charge will get compensated by removal of one of the hydrogen. So that is why you will have a NH2 at this position rather than ammonia. So similarly, you will get this SO2 NH2. So this is a very simple reaction in which ammonia will displace your Cl. So now coming at this reagent R. So in the reagent R, what they have done is they have done the cyclization. So they have used it for NO2CA3, sodium carbonate and KMnO4. So based on the final product, there should be a oxidation which is to be done of this methyl. So what can do the oxidation, KMnO4 or the sodium carbonate?
Wonderful.
KMnO4, right? Yeah. So basically KMnO4 will do the oxidation. So now what will happen here? You can see here this is the expanded version of the second species which we are getting. So after oxidation, this methyl is converted into the acid. So after converting into the acid, what will happen? This amine having the lone pair of nitrogen. So this lone pair will attack on the carbonyl carbon and it will form this kind of species. So here there is a positive charge that is generated at the nitrogen and a negative charge. This is the tetrahedral intermediate which is getting formed. So this O minus when come down, this OH will leaves out. So after that, the OH minus which leaves out here will abstract the proton from the nitrogen to form a neutral molecule, that is water. So here you will get the formation of saccharin. So this is how it is done. So first of all, what will happen? Toluene will give you a electrophilic aromatic substitution with this acid to give you this SO2Cl substituted ortho product. After that, ammonia will displace chlorine to get the amine. After that, the oxidation of methyl will take place to form the acid, and the intramolecular cyclization will take place to give you saccharin. So, is it clear to all of you how P, Q, and R reagents uh, are required in the synthesis of the saccharin? So, is the mechanism clear to all of you? Any doubts? Any queries? Any queries, guys?
Clear. Ma'am.
Clear. Okay. Fine. Okay, if it is clear, then I'm moving towards problem number 8. So in problem number 8, they are saying what is the percentage distribution of the elimination products formed in the reaction given below. So this is the reaction, and you have to find out the percentage of the formation of first and second. So elimination reaction can happen in both the ways. How it can happen? Either this proton, this proton can go here and this will go out. Either this will go here and then this will go here to, and Br will leaves out. So there could be two possibilities of the elimination, either this way or either this way, right? Because Br is present at this position, so either this proton or this proton that is present at alpha can go to form the double bond and Br will leaves out. So in first possibility, that is this possibility. First possibility is the removal of proton from this side. So this is the first possibility. So this is how it is going here and Br will leaves out. The second possibility is this. So hydrogen is going here and Br will leave out to give you this second product. So this 1 and 2 product is possible by the elimination of this proton by sodium ethoxide. This is a base. So now you have to identify the percentage distribution of elimination products. So which product will form in which percentage? Basically, this is a rough percentage you have to identify. So they are asking in first option 50-50%, both of them will form. First will form in 0% and second is form in 100%. Third option is 60% one and 40% two. And fourth option is 100% one and 0% two. So can anyone tell me which could be the correct percentage?
The last one.
The last one.
Option D.
Option D. So why option D is the right one, guys? So here what will happen, I have
Uh,
told you previously, according to the Brett's rule, the the double bond at the bridgehead is highly unstable. So, according to Brett rule, the double bond which is to be formed at the bridgehead is highly avoided. So that is why the second option, that is the second elimination, is highly unfavorable than one. So if you have a choice that the alpha proton is abstracted from one side and two side, there will be 100% of the favorability of abstraction of proton from first side rather than second, because second forms a double bond that is present at the bridgehead position, and according to Brett's rule, the bridgehead double bond is highly unstable, highly avoidable. So that is why your second will be in 0 percentage if it has a choice, and first will be forming as in 100%. So that is why fourth is the correct option. So is it clear to all of you why fourth is the correct option? Anyone has any doubt in this?
No, ma'am.
Okay, if there is no doubt, then I'm moving forward. So problem number 9. So in the problem number 9, they're asking which is the main product of the following reaction. So guys, this is a very straightforward reaction. So first of all, they are added sodium hydroxide, sorry, sodium ethoxide, sorry. So sodium ethoxide and ethanol. So sodium ethoxide is a strong base. It will abstract the acidic proton. So acidic proton is present as it is a symmetrical molecule. Acidic proton is present at alpha position of this both of the ester. So as it is a symmetrical molecule, abstraction of hydrogen at from any of the position will take place, right? So after the abstraction, what will happen? If abstraction is going to take place from this side, then what will happen as you have a nucleophile in the reaction, as you have nucleophile in the substrate and also the electrophile at the similar substrate. So intramolecular cyclization is possible because you have nucleophilic and electrophilic both the sites present in the same substrate. So here after the cyclization, this 1, 2, 3, 4 and 5. So basically 5 membered ring is get formed after the cyclization of this nucleophile with this electrophile, which is the driving force of this reaction because 5 membered ring is highly stable, and that is why after the cyclization it is going to give you this kind of tetrahedral intermediate. And I have told you that OET is a good leaving group. So here alkoxide will come down and OET will leave out to give you this product. So this is to be done after the hydrolysis. So basically in the first step sodium hydroxide will take up a proton, then the intramolecular cyclization will take place to give you this, and in the hydrolysis step this alkoxide will come down and your OET will leave out to give you this ester compound. So is it clear? Is this much clear to all of you, the mechanism? Can anyone tell me which is the, it is actually a name reaction. Can anyone tell me which is the name reaction this is? Sorry?
Aldol procedure, fertilization.
Aldol. Okay. Aldol cyclization. Or we can also say na, that it is a Dickman condensation. So be precise. Aldol is one of the reaction, but generally, if the cyclization is going between the esters, then we say a Dickman condensation, right? So this is an example of Dickman condensation reaction. So the correct option will be option number A. So is it clear to all of you how the mechanism is going?
Yes, ma'am.
Okay, fine. So moving towards the problem number 10. So in problem number 10, they are asking which of the following reactions show a correct main product. Okay, so they are asking in these four reactions which is the correct product. So one by one we have to go through these reactions. So in first reactions, now they have given you two molecule of this ester and they have again treated in the same condition which we have seen in this case. These are the two esters and they have treated it with sodium ethoxide, ethanol, and again hydrolysis. So this is the example for again the Dickman condensation. So what is happening, guys? So it will abstract a proton from the alpha position of this carbonyl carbon. So this is how it is happening. So abstraction of proton will takes place. Then the attack at the again the carbonyl carbon of the similar molecule because you have two equivalent of this molecule. So one anion is getting generated and it is attacked on another molecule of the same species to get you this tetrahedral intermediate. So after coming down this tetrahedral intermediate, OET will knock out. So after knocking out of OET, you will get a diketone compound which is looking like this. But in your product, this is a straight chain. But in our product, what is happening? This methyl is at the second position. So that is why the arrangement of these carbons at the in the product is not correct. So basically here also the Dickman condensation is taking place, but the arrangement of the abstraction of the negative charge, that is the abstraction of the proton, sorry, is from the beta side. So which is a wrong thing. Alpha abstraction is taking place instead of beta abstraction in our product, and here the beta abstraction is taking place. So that is why arrangement of the carbon is getting faulty here, but it is not matching with our product. So is it clear why the first reaction product is wrong and our product is getting a secondary methyl? Is it clear to all of you?
Yes, ma'am.
Okay, so first reaction is wrong. So here the main product is wrong. So this is not the product which you are going to get from this reaction. So now coming to problem number B. So here they have treated it with lithium dimethylamide and THF. So basically it is also a LDA kind of species with methyl instead of isopropyl group. So I have already told you about the kinetic and thermodynamic enolate. So now you have to tell me that is the B reaction right or not? Is the outcome is correct or not?
No. Incorrect.
Incorrect.
Wrong.
Because here at low temperature I have told you that kinetic enolate is going to be formed. So kinetic enolate is what? Less substituted enolate. So double bond should be here instead of here. So negative charge, that is the abstraction of proton, will takes place from this position rather than this position. In the case of low temperature, kinetic enolate is going to be formed. So this is the wrong product. So this is the wrong product. So coming to option number C. Now tell me, is it right or not?
Yes, ma'am.
Correct.
Yeah. Why? Because
Yes.
here what is happening, base in THF but 20 degrees centigrade. So here instead of the low temperature which is in minus, there is increase in temperature. So at high temperature I have told you thermodynamic enolate is stabilized. So here thermodynamic enolate will form. What is thermodynamic enolate? The abstraction will take place from this position and a double bond is going to be developed at this position, that is more substituted site. So thermodynamic enolate have the double bond generated at more substituted site, whereas kinetic enolate has the double bond generated at less substituted site. So this is the right outcome. Okay, now coming to fourth outcome. So is it right or wrong? Anyone tell me?
Wrong numbers.
Wrong. Why wrong? Because guys, what is happening?
Because
Yeah,
yes, in benzene, the bromobenzene, we have double bond factor. So nuclear precursors are not possible.
yeah.
This.
Very nice. So here what is happening guys, if you see this you will think that yes, this attack is feasible and it this Br will knock out and this pH will substitute at the alpha position. It visibly it looks like yeah, it is possible. But if you go in the sterics, then you will realize that it's the bromobenzene. Okay. And bromobenzene being a aromatic benzene, so here this CBr bond is having a partial double bond character because of the delocalization. And I've told you that if having a partial double bond character means that the carbon, the CBr bond length is shorter and it is less reactive. So SN2 reaction at this bromobenzene is not possible as it is. So in this condition it is not going to be happen. So that is why this is a wrong outcome. So option number C will be the right one because you have to identify the correct main product. So correct main product is happening in the option number C only. So is it right to all of you? Is it understood? Is it clear?
Yes, ma'am.
Okay. So moving towards, so here also you can refer this the kinetic enolate and the thermodynamic enolate. Okay, I will upload this slide on the YouTube channel, you can go through it. So coming to problem number 11. So here also it is a very simple question based on the previous concept only. So they are asking this ketone, they have treated it with LDA minus 70 degrees centigrade. After the formation of enolate, they have treated the enolate with methyl iodide to give you B. Now quickly tell me what is A and B. Can anyone tell me what is A and B? Based on the previous things which we have discussed, LDA at zero at lower temperature will give you a kinetic enolate, and after that, this enolate is subjected to
Option A.
option A, right? So here,
First option. First option.
first option. So here, what was happening? A kinetic enolate is getting formed, which is this. After that, it is treated with methyl iodide. What will happen? This oxyanion will come. Sorry, this oxyanion will come down, and this double bond will attack on the methyl, and iodide will use out. So here, at the alpha position, methyl is getting substituted. So option number A is the correct one. So now coming to, this is how the mechanism is going. Basically, negative charge, then enolate formation and methyl trapping. So now coming to problem number 12. So which of the following statements about keto-enol equilibrium is correct? The enol form is less stable than corresponding keto form. The enol keto equilibrium can be catalyzed by base. Enol keto equilibrium can be catalyzed by acid, or all of the above. So basically, this is the keto form and this is the enol form. So these are the tautomers. So this keto form is preferentially more stable than enol form. And if you have to be, if you have to form a catalyzed cycle between this enol form and keto form, so what will happen? If you have an enol form, this H ion in the acidic medium, H ion is getting abstracted and a carbon is getting a positive charge. Here the positive charge is getting generated because of the lone pair can come down to stabilize the positive charge. So here, this is the protonated carbonyl system, this is the resonance form which is forming, and this keto form can get generated. Similarly, in the basic medium also, you can convert enol form into the keto form. But abstraction of the proton of this OH, and then this alkoxy anion will come down, and this C minus bond is getting generated. After that, this base will give the proton to neutralize this negative charge to give you the keto form. So this is how the enol form can be converted into the ketone form by the acid catalyzed or base catalyzed method. So can anyone quickly tell me which is the correct option?
Last option. Option
Last
D.
option. Because I have told you that keto form is highly stable than enol form. So this is the right option because enol form is less stable. Keto-enol equilibrium can be catalyzed by base and acid. I have showed you how it can be catalyzed by acid and base. So these two also are the right option. So all of the above are the correct option for this. So is it clear, guys? This much?
Yes, ma'am.
Fine.
Yes.
So coming to problem number 13. So here again, it is a very simple question. So basically, they have to you have to identify the major product of the reaction. So you have to identify this P. So coming to first step, they have treated it with LDA. So LDA, what it will do, it will abstract a proton. So will it abstract a proton from this side or this side? Tell me which is stable.
Left side.
Let's say
Left side, right? I have to mark it A or B. So is it A or B?
A.
A. So LDA will abstract a proton from HA position. Why? Because if it abstract from HB, you will get a negative charge at this position, and this would be a vinyl anion. So vinyl anion is very unstable. Instead, unlike the allyl chain, the vinyl anion is unstable. Whereas if you see this kind of system, if this negative charge is present at this carbon, that is the allyl carbon, then it is stabilized due to the delocalization. Right, this is the delocalization which is present in this system. But in the vinyl system, there is no delocalization. So here, the negative charge is sp2 carbon, because sp2 is also electronegative carbon. So here it having the high s character sp2. So that is why your negative charge is getting destabilized at this position. So here the abstraction will takes place from the alpha position, which is this alpha. So after the generation of the carbon ion, next step is the alylation. So now tell me, the alylation is taking place at carbon number 1 or carbon number 2?
One.
Carbon number
One.
1, because of the leaving ability of this halogens.
Yes, iodine is good
Yeah.
living group than fluorine.
So iodine is a good leaving group, then chlorine. That is why your negative charge is now attacking on the carbon number 1 rather than carbon number 2. So it will displace your iodine and you will get the product. So what is the correct product then? Option number
3.
Third.
third will be the correct option. Okay. So now coming to problem number 14. So which is the main product of the following reaction? So now you have to identify the main product of this reaction. Now this is the aldol condensation reaction. So here, first of all, the sodium hydroxide will abstract a proton. So from where it will abstract a proton? Benzaldehyde or acetone?
From acetone.
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 Because benzaldehyde doesn't have a alpha proton. So it is,
Alpha hydrogen.
yeah, it doesn't have a alpha proton. So that is why it is going to abstract a proton from the alpha position of acetone, and this is how it is getting generated. After that, it will attack on this carbonyl carbon to give you this. So here in our case, you can write it as this also, this alkoxy, but you have water molecule that is present. So here in the basic medium, you have water molecule. That is why instead of O minus, you have OH. So here the second step is hydrolysis, which means a dehydration step has to be done. So a dehydration step is going to be happen in this case, and you will get a double bond at this position. So now if you are having a double bond at this position, then these two options can be possible, C and D. So now tell me, which is more stabilized, C or D?
C.
C,
C1.
because of the trans double bond. So here the trans,
Steric hindrance.
yeah, because of the steric hindrance between this phenyl and COCH3 bond,
Yeah.
it will prefer to be trans rather than cis. So a more stable trans alkene is what you will get rather than the cis alkene. So here you will get a alpha beta unsaturated carbonyl compound with trans geometry. So option number C will be the correct one. So is it clear, guys, the mechanism of this reaction?
Yes, ma'am.
Okay, fine. So we are going to problem number 15. So in problem number 15, they are asking which enol form of ethyl 3-oxobutanoate is predominant at equilibrium. So now in between of these four forms, you have to identify which enol form is predominating at the equilibrium. So which is the more stabilized form? This is the core structure of ethyl 3 oxobutanoate. So now can anyone quickly tell me which could be the most stabilized structure? Most stabilized structure. Any guesses?
I think B.
B. Any other answer than B?
C. I think C.
C. Okay. So guys, what is happening in the first option? As you can see, there is no delocalization that can be possible with this ketone because of the exocyclic double bond. So that is why this form is not the stablest form, right? So it is not the most stable form. So coming to a problem, option number two. So here, if this lone pair will come down, you have a delocalization with this carbonyl carbon, right? In this case also, the similar form is present. So here also there is a delocalization in the similar way, but there is a thing that is it is a cis double bond and it is a trans double bond. So can anyone tell me between this B and C which is more stable?
Trans.
Trans. Okay. So if trans is more stable, guys, then you are obviously eliminating one possibility here. Can anyone see any other interaction in these two cases?
Hydrogen and drugs.
Yeah, hydrogen bonding. So there is a hydrogen bonding that you have to also take care before answering. Here there is a hydrogen bonding which is present in the case of cis, but it cannot be possible in the case of trans, right? So that is why it is giving, instead of the cis geometry, it is giving the additional stability to your cis double bond rather than the trans double bond. If there is no hydrogen bonding, then you can say yes, the trans double bond is the predominant at equilibrium. But there is another thing that is the hydrogen bonding, which is responsible for making your cis double bond more stable than the trans double bond. So basically, option B will be the right one. So here, this form of 3-oxobutanoate will be predominating at equilibrium. So is it right to all of you? Is it understand? Is it understood? Any queries? Any questions in this question?
Yes, ma'am, understood.
Okay. So if it is clear, then I'm moving to problem number 16. That is, isoform reaction is a confirmatory test for the compounds having COCH3, methyl, amide, or acid.
First.
First,
First. One.
yeah. So it is a well-known reaction, that is the isoform reaction, which is confirmatory test for the ketones. So what will happen in the reaction? So in the presence of base and CHCl3, that is chloroform. In the presence of base, this alpha hydrogen is getting abstracted and this alkoxide ion will trap the iodine. So this iodine is getting trapped and again this hydrogen will become more acidic in nature because of the iodine electronegativity. So here these two proton one by one is also getting displaced by iodine, and after that again the base will attack on this carbonyl carbon, and after this tetrahedral intermediate will get collapse to give you this CHI3 and ketone and acid, sorry. So it is possible in the case of ketones only, so it is a confirmatory test for ketones. So the option number A is the correct one. Okay, so it is the basic question. So now coming to the last problem of the session, that is problem number 17. So in this question, you have to identify the missing reactants or products in the following acetyl protecting group reactions. So this is basically the protecting group reactions. So now you have to identify this product and this reactant. So now coming to first. So now what is happening here, guys? Now tell me, in between ester and ketone, this acetal protection will be happening of which? Like ester will get protected or ketone will get protected?
Ketone,
Okay, ketone
ketone will get it.
getting protected. Ketone or ester? Ketone, na? Okay. So
Ketone.
why ketone? Because guys, what is happening? You have to identify the electrophilic character of this carbon because you have lone pair of oxygen. See here, there is a nucleophilic attack which is going to be happen at this carbon. So now that carbon will be getting attacked by the oxygen lone pair, which is more electrophilic in nature. And previously, I have told you that ketone carbonyl carbon is more electrophilic than the ester. Why? Because oxygen lone pairs here is present in the delocalization with this ester, which is making this carbon less electrophilic than ketone. So that is why this oxygen lone pair will attack onto this carbon and giving you the protected diol. So now tell me what will be the correct option for option number one? For the action one only I'm asking. So here there is a protecting group that would be getting attached to this carbon. Fine. Instead of ester, you are having the protection of ketone. So now coming to option now reaction number two. So here you have to identify the reactant. So you are given the product. Now you have to find out the what is the reactant. So in this case also you have a protection. So can anyone tell me what would be the reactant here? It would be a ketone, diol, what it would be based on the options.
Ketone will
Ketone.
be ketone.
Yeah. So similarly, as we have seen here, the protecting group ability is having on basically on this ketone. So here also this ketone is protected by the diol rather than the diol. Rather having the diol here, you will have a ketone here at this position. Okay. So diol, this is the correct. This is obviously not the case because diol is not going to protect diol. Here diol and ketone. But if you protect this diol with this ketone, you are not going to have that particular thing because you now have a additional methyl groups, which is not present in this case. In this case also, this is not going to happen. Diol, it is not going to give you the protection. So you are only left with option number one. So in this case, first option is the protection of the ketone. In the second case, again the protection of ketone is taking place. So option number one will be the correct one. So is it understood all of you? Any doubts?
Yes, ma'am. Yes, ma'am.
Okay. So I'm done for today. This was the last question and we have done it. So I'm just closing the session now. So thank you so much guys for joining the session and be patient because my connection is very poor today. So thank you so much. So I'm
Ma'am,
stopping the recording.
ma'am, where we will
Thank you
get
very much.
Sorry.
previous session, where we can get previous session.
So I have actually uploaded it on the YouTube channel, which is operated by me. So
So which channel?
channel, yeah.
Mhm.
So I'll share you the
Can you,
username in the chat box. Please copy it for the purpose. So this is the name of my YouTube channel. I have pasted on the chat box. So you can go through it and you will find all the videos. Okay?
okay.
Okay. So thank you guys for joining. I'm closing the session. Thank you so much.